All right, go. So I have just posted the lecture. We're starting review of linear algebra. Now, how many of you have already had linear algebra along with your differential equation? And the rest of you are in that course right now? Okay. So you will be reviewing this, I guess, twice, one way or the other. And since we know that so I apologize if some of this is boring and you've already seen it. It's pretty speedy review, but what we really need out of linear algebra, so linear algebra is one way to deal with data and overall, so we have done. So our motivation is to deal with data and better yet, figure out how to employ computers to deal with data and then solve problems with them. So your first problem overall is how to kind of load data into some sort of structure that you're going to be able to manipulate. So one way to think about data is this array of numbers. And then you visualize array as a row array or a column array that can be motivated by the problem itself. But these one-dimensional arrays of vectors are one way to store the data. You could also go multidimensional, so you can actually keep going. So you can have two-dimensional arrays and more than that. So can you think of some data in petroleum engineering that comes into one array? Well data. So any type of well data. So well logging, right? So well logging, what type of well logs do we have? There was that introductory class of petroleum engineering that should mention something. Is that still stored somewhere? Porosity log. Okay. So first thing is that I have to know I have a rock, right? So where do I store fluids? In voids. Well, how much of those voids do I have now? There are different types of porosity logs. There's neutron porosity log. So I bombard my surface with neutrons and kind of listen to what comes back. That's how everything works. Rather knock on it than listen back, which is the DBS log, like the shear waves and so forth. So there's different types of logs. And what is the typical spacing between the information, spatial spacing between the information? So half to a foot. So foot is common. So every 1 foot of depth, I have a piece of information. And that piece of information is a number, okay? Regardless of what it is that I recorded. So I record multiple things. So now that number will be, this stream of numbers will be a vector. Most of the time, as we're like playing the things, we're going to have these vectors where like I have 3 numbers and then 1, 2, 3 as a column, right? Or 1, 2, 3 as an array. They're just playthings to work with, just so that we understand the concepts. But you should visualize yourself long vectors, 3,000 plus long, that have information every 1 foot that is relevant to the problem. And you want to manipulate, you want to do something with that. What you want to do, you will actually be learning for 2-3 years about it, right? But that's the essence of that. So linear algebra is trying to kind of abstract away. It's not concerned whether you're a petroleum engineer, electrical engineer, chemical engineer, whatever type of data you might be having. Okay? But it's concerned about, like, let's come up with some abstract rules and ways to deal with all of that data. And then you, as an engineer from a specific field, put meaning to that data. Math is not putting meaning to anything. Math is just dealing and trying to be as abstract as possible. So that's where linear algebra comes in. And you will learn that actually in differential equations, linear algebra in dealing with matrices is very useful as well. But essentially in petroleum engineering, it's just like dealing with massive amounts of data. So we simply want to, at the very basic level, we want to be able to add, subtract, multiply these vectors and matrices. So I mentioned vectors. Any idea of what would be the matrices? Some data that actually just like an array of U that has rows and columns. Okay? What type of data would have that arrangement? And it could be related to the spatial, actual spatial arrangement in reality. What surveys are there? What's the very first survey we do before we drill?
Wall survey. Yeah.
Before that? Trucks that go and do this.
Seismic.
Listen back. Seismic. Okay? So seismic, you have thumper trucks. They go and literally, first they put a spatial arrangement of geophones that are listening. And the thumper truck goes and produces a pressure wave. And then those geophones are listening back. And based on how they reflect, they try to reconstruct what's down there. So typically larger faults or breaks in the surface of some kind will reflect those waves back. And that's how you reconstruct or attempt to what is that. Okay. So geophysicists typically deal with that part. So since you have an area that you're surveying, okay, you're going to have the data to this area as well. But there is also the depth information these days. So there's sort of 2D and 3D, 3D and 4D seismic as well. So you can have multiple dimensionality. Anything else could be, just if you think about this room, it's three-dimensional. If I had some measurement of the air quality and I wanted a spatial measurement of that air quality, I could technically put an instrument in various places in this room. And each instrument would give me one data point. And if that has some sort of spatial meaning, then I'm going to organize it in a matrix that mimics that spatial order. And those are my multiple dimensional arrays. So we might have these matrices in 2D, 3D, and so forth. And these days you will hear a word, big data. Has anybody heard that? What does that mean? Now with big data, what it means is that we're collecting more and more data, typically also in time. So at every time point, you're going to have multiple measurements. So for instance, when you're drilling, you have a rotary bit, and that rotary bit is smart bit. It sends the data back. When it's smart, it has a wireless or some sort of connection, wired often as well, because wireless that doesn't work all that well, right? But it's sending information back. And if this data is streamed back constantly, and I have a lot of it, then I simply have like a lot of these numbers and vectors to deal with, and that's referred to as big data. So any data, any type of data can be big data. Okay. Since I'm on Facebook this morning, I'm not advertising it at all, actually. Don't like it to an extent, and I like it at the same time, so that we have a love-hate relationship that way. So essentially, there's for every account, there is multiple data and information depending, and some of it could be also images. Each image, this image that you see, is actually when I zoom in, I will actually see a raster plot. So it's like there are dots. And there's a resolution of the screen, and that's a two-dimensional array as well. Two-dimensional array with red, green, and blue that create the color. Okay? There's actually 3 arrays of this size, and how big is the size is actually, well, I'm not going to count how many I have, but I think it's about, my screen is about 1400 by 800 or so. So you get the idea of the size. So all of those we have to manipulate. And there are certain abstract ways, like addition, subtraction, multiplication, transpose. How do I flip? If I want to flip the screen, right, I can literally do it in multiple ways. I want to also figure out what is the essence, and we have this linear combination of vectors. So if I can express one vector as linear combination of others, that reduces the amount of information I need to store. And that can actually help me out. And then there's dot products, determining whether two vectors are orthogonal or orthonormal, and using norms to actually compare them. So we're going to first review all of those operations, and then we're going to learn how to import it into an actual software that we're going to use, which is called Python or programming environment. And maybe you will, during this class, I have posted these materials. Don't be scared of this MATLAB. We're not going to be learning MATLAB and Python in this class, just Python, but it happens that this book has a pretty good review on matrix linear algebra. So maybe will post this chapter for you for your reading if you prefer to read the book as opposed to the slides. So let's get going. So just to formalize, I can have, this is a column vector, and I can have a row vector. How do I align them is somewhat up to me. We will also learn that how then I store it into a computer is completely different. So math likes being strict about whether something is a column or a row, because in essence it looks at this one vector, which is one-dimensional vector, and says so this is my matrix that has m rows and only one column. Okay. And this is a matrix that has one row and n columns. Okay. But that's a choice of viewing it that way, and in certain mathematical operations, it's actually really useful to do so. As far as computer goes, computer thinks like, okay, where do I squeeze n numbers? Where do I squeeze n numbers, right? So it doesn't matter in which order they are, as long as they're somewhere in the neighborhood so I can replay. So computer has a different problem. It's like, okay, I have these pieces of information. What is the effective way so that I put it in memory and then I also refer to it? So slightly different programming environments will find a slightly different way. So that's something that you just have to conceptually understand. There's like, how do I do things in practice? There's what math is telling me to do, and then like, how do I actually do it? So we will refer to scalars as alpha, beta, gamma, or most of the time, and to vectors as this lowercase Roman letters, and matrices as uppercase. Does it matter what we do? Not really, but this just keeps things a little tidier. Okay. So vector operations, some of them are kind of intuitive. So if I had two vectors, so these are two column vectors, I have 3 numbers for each. Their dimension is 3. How would I proceed to do addition? How would I have to define addition?
Straight across.
Straight across. So basically,
if they're the same size, you just go straight across.
First check, that's a great comment. I have to see whether they're same size. If they're not same size, they're not objects I can add. They technically belong to 2 different spaces. Okay? So it's basically something in 2 dimensions has only 2 numbers. I don't know how to add 2 dimensions in the 3 unless I mentally extend 2 dimensions to 3 and add some zeros to it. Okay? But unless I do that, so I basically embed, if I have 3-dimensional space, okay, this plane, the 4, is part of that space, and its dimension z is 0. Okay, it's on the floor. So I can definitely have a way to embed, but if I don't embed, then formally I don't know how to add things from this floor to my entire room. So basically we do have to have the same dimensions, and then we will just go dimension by dimension, which is where I put things is important. So 2, 1, 0 is not the same as 1, 0, 2. So where I put the numbers. Why? Because in practice, if I had a bell log, that location, first, second, third, refers to the actual embed. Okay, so it is important to know where is it that I have porosity so. Is it 3,000 feet or 4,000? Okay? So in that sense, I have to know what the order is. So what is the result of this? Can everybody just click so that you activate your, write it down? 1 to 5, we've already done that. Okay. I'm asking 2 easy questions. So addition and subtraction would go this way. And multiplication by scalar, how would I do that? So if I now actually want a scalar, number 2, okay, and I wanted to multiply this first vector with it, okay, and then, so this is my now generalization, if I had alpha times a vector plus beta times another vector. Then what I'm going to do is I'm going to multiply every location with this scalar. Not just first, not just second, that would be kind of arbitrary. But I'm going to have a row where we're going to multiply them all, and then I just add two vectors. So basically, this is my linear combination of two vectors in a formal way. So here are some examples. Let's do. So everybody first jot it down. Perform the operation if you can, and if you cannot, then don't do it. Can I do the first one?
Yes.
Yes. So that one's easy. So it's 2 plus 3 times minus 1 in the first spot. I'm going to get 2 minus 3, which is minus 1. And then I have 1 plus 3 times 1. Don't forget to multiply that one. So that's 1 plus 3 is 4. Okay. So there's going to be minus 1 and 4. And then can I do the second one? No. So this is where I have a problem with dimension. So I'm going to actually tell you, though, that your computing environment might be smarty pants and actually perform this addition. So math formally says no. But the way it is implemented in computers, often just to shorten typing, is that this number 3 will be added to both locations. Okay? So we have to mentally understand that there is abstractions and formalisms, but there is also how they're implemented. Okay? So in practice, this will often, if you type it into a computer, fly. Well, you don't type just this, but you type it in a slightly different way. But it actually can fly. Same thing here. Formally, this should work because this is a column, this is a vector, yet they have the same number of elements. And there are some computing environments that are like, oh, that's all one dimension. We don't recognize column versus column versus row. So the fun part. So this class used to be in MATLAB. Now it's in Python. So if you type this in MATLAB or Python, it's actually going to perform this operation and add 3 to both, even though formally math says no. And then in this one, this will not work in MATLAB, but it will work in Python. Because Python says everything is one dimension. I don't care how you call it and how you organize it in space. There is no space in one dimension. Okay? So again, implementation is something to think about. And I'm warning you ahead of time because that's typically this getting used to, sort of like how things are done, is typically this initial friction in learning anything. So we will learn Python. Python is chosen because it's right now one growing language that is kind of omnipresent. It actually increases your chances of an interview. You have Python in your CV. So we have decided, all right, we're going to switch. But technically, conceptually, you can learn any programming language. So don't let that stop you, especially with all kinds of online tools that we have. So don't let that bound you. You're going to learn one, and maybe you have learned already something. Who has learned Java? Some people have done Java. Any other? C+ even? Okay. So you might have learned some other. Okay. Python and C and C++ are kind of regarded as the core type, and MATLAB resembles them as well. So basically, that syntax is kind of only present in a lot of languages, so you can apply it easily. It's just that there's this friction, like, okay, how do I actually type things in and what it is that comes back. So again, there's formal. So if you're confused in homework, just write down, I think that mathematically this doesn't fly because I have a column, so just explain. Because sometimes technically it can go both ways. All right. So we need to also figure out an inner product. Okay. So I can define for two vectors an inner product. And right now it's an abstract concept, but it actually helps us to measure angle between two vectors, among all other things. So technically, if I'm going to apply this formalism of having row vectors and column vectors, then I can actually think about this as a matrix or matrix vector multiplication. And in that case, I have to have a row vector times a column vector. And the way I'm going to define my inner product is x1 times y1 plus x2 times y2 plus x3 times y3 plus x4 times y4. So this is in case that I have 4. If I have more or less, I can keep going. Now, if I actually write that, and I'm going to introduce a funky symbol here. Has anybody seen this symbol? Sigma. Okay. So this is uppercase sigma in Greek, still used today in Greek. But there's math is full of Greek letters. It's actually really useful to learn Greek alphabet. Know it. Okay. So it's used for summation. So this big sigma means that I'm summing all things that look like this, but go for I is equal to 1 to n. So I'm going to first replace it by 1. I'm going to have x1, y1. And since sigma is summation, then I'm going to say plus. I is equal to 2 gives me x2, y2, plus x3, y3, plus x4, y4, all the way however many I have, generally n. So this is basically a shorthand notation for this. 4 of them is not a problem to put together. We need computers to work with hundreds or thousands. Then I'm not writing by hand. Okay. So this is, we're going to practice a lot of sums like this, and we're going to be translating them to code very soon. And that's why, because I want an effective way to write down how to sum thousands of things, because as we learned, I don't know of a Verilog that only has 4 entries. Okay? Verilogs typically have a little more than 4, just a little. What is the longest well? Is that the one in Russia that has 30 kilometers or so? 30 kilometers? Translate that to feet and then put one number every 1 foot. Okay? To get the idea. All right. So for those, we're going to not write that x1 plus x2 plus x3 and keep going. Okay? All right. Now, norms for vectors are trying to compare. So now I have this vector of numbers. I need to figure out, well, how do I compare it to some other vector? We can do that in multiple ways. So if I had just numbers, just 2 numbers, we can just compare them. So I have 2 and 3, and 2 is less than 3. Now if I have 2 and minus 3, I first have to decide, well, is this minus important? So if I'm talking about temperature, it is. Minus 3 is definitely less than 2. But if I'm talking about something else that is just like a question of distance, okay, and this minus just refers to going south as opposed to north, well, what it is that I'm going to do, if all I need to prepare for is have gas to drive certain distance, then I don't care in which direction, I just need gas to cover that distance, right? So in that sense, just absolute measure is fine. So we often just look at the absolute value and compare things in terms of absolute value. Now, what do I do if I have actually a large collection of numbers? Then I take absolute values of every element and figure out different ways how I could basically digest them into one number. So you have seen that already in Euclidean distances. So if I just have a vector in space, in two-dimensional space, so this one is a 3, 4. Then if I'm just looking at the length of this vector, I need Pythagoras and his beautiful theorem to tell me that its length is square root of 3 squared plus 4 squared, which is 5. So that gives me this length of vector in 2 dimensions and 3 dimensions in our actual space that we typically work with. That gives me a way to compare things and actually generalize. So in physics, we're going to call this, if this was a displacement, we're going to call, or a velocity vector, we're going to call the actual magnitude of its speed. So velocity has a direction and it's actually a vector. Speed is just a number. So if I'm a traffic officer looking to give somebody a speed ticket, all I need is speed. So I'm going to compare cars and their vectors by speed. So this comparison is how I'm normalizing things first. So we're referring to this speed as a norm. Okay. Now this is so-called Euclidean or L2 norm. Those are just fancy names for this simple one. So I can actually generalize it. Okay, so if I have more than 2, I have any n numbers, I'm going to take each number, square it, add them all up, and then take the square root. Okay. And that's one way to have a so-called Euclidean L2 norm, 2 norm. There's a number of ways. Now, math is funny in the saying that mathematicians step back and say, well, what differentiates 2 from 3 or 4 or 5 or 7 or 7.5? Why don't we just define norms for any number? Technically, you can define any norm, okay? So you can do a cube of x1 plus cube of x2, actually its absolute value, and then to the 1 over 3. Or the 4 or 5 or whatever it is. We're going to take it. But just to let you know that there's a way to generalize this, and it's actually useful in some applications and in also analysis. Now, if I was thinking about vectors as rows times columns, then I can actually do this as a transpose of a single vector. So if I had a column vector, its transpose would be the same vector, just in a row position. And then I can do those row times column thing, which is this, what's written here is the same as this. So that's just another way to formalize. So this is this P, because math says, well, there's nothing special about 2. I can do it for P. Now, if I wanted to do it for 1, all I will take is just absolute values of all numbers and just sum them up. There's no 1 root. I'm just not doing anything. It's to the power of 1. So just sum of absolute values is so-called 1 norm. And then if I let this P keep going to infinity, what happens if I have infinite numbers, technically infinite, if I have infinite power, then the largest absolute value will simply overpower them all, and the others will not apply. So technically, this ends up just being the maximum of all of the numbers that I have in there, absolute value. Usually, if you let your mind on it. So if you have that number out of 200, P is 200, okay? Or 300. As I get to larger powers, that very largest number in absolute value to whatever large power We'll kind of take it all. I call that snowball effect. And the others will just be too small as you go to infinite large value. So technically what we call infinity norm for this p is equal to infinity ends up being just maximum of all of these values, because I'm going to take a power p and then I'm going to do to 1 over p. Cool. So let's now take this simple vector 1, 2, take a piece of paper and compute Euclidean or 2 norm, then 1 norm, then infinity. And if you're bored, let's give you a larger vector. See? The problem is when you complete something, you get more to do. So let's do 3 minus 1 and 0. Everybody follow that? So basically, my 2 norm would say take 1 square plus 2 square, that's 5, and take the square root of it, the square root of 5. My 1 norm would say just take absolute values and add them up. So absolute of 1 plus absolute of 2. And then the max norm or infinity norm, just take the maximum of them all in absolute value, which is 2. So that's for this vector 1, 2. If I had this vector, then 2 norm would be square root of 9 plus 1, so square root of 10 plus 0. The 1 norm will be 4 because it's just absolute values of these. And the infinity norm is 3 because that's the largest number in absolute value. Now, what is the actual practical use for these? Do I ever, for instance, 1 norm, can anybody imagine how would it be helpful? In distances. If I was going to go to that corner, to that door, can I fly? I'm not that good. So the distance I'm going to cover is not going to be Euclidean distance. The distance, and if I need to estimate gas or whatever muffin that I ate this morning to give me energy, I gotta go this way, and then I go up. Yes? So what is that distance in terms of the norm that you just learned? 1 norm. Absolute value in whatever I have in y direction going, plus absolute value in whatever I have in x direction going. Yes? That was a nice walk. Okay, so I suggest you all do that if you if you need a stretch. So there are different norms that are useful for different things. So there's also, for instance, here we're in Austin, and there's all these drought conditions, and engineers need a way to alert the entire city when the drought conditions take place. And what they do is that they actually have, and actually they have these things online. You can monitor every lake around this city on LCRA, Lower Colorado River Authority website, and you can monitor their levels. So what they do is they feed in those numbers every morning, or probably they do that every hour, or something, and they sum up the levels. And then when those levels, so that's also sort of an absolute value of sorts, or they look at the differences of what it should be. So when that falls below a certain level, there's this alert. So we need to go to this and this restriction and not water the lawn and so forth. So those are engineering decisions that need to be made. So for that again, my L2 norm is not that useful. However, if I'm flying, then yes, L2 norm is that. So different cases, basically in this case, it's actually sum of the volumes of the lakes, but knowing the area of the lakes, you will figure out the volume, right? by doing that. So basically there's a threshold, and then you figure out what do you need to water. I actually have even simpler engineering decision in my life. I just don't really water my lawn. So I have the landscape that survives me. So anyway, so again, this is just to formalize. So if you were actually driving on a regular grid, okay, then your L1 norm is just actually sum of absolute values wherever it is that you're going, regardless of the route you really take. Right? If you look at all of the segments that are horizontal versus all of the segments that are vertical, you would get actually L1 norm. All right. There's just a little longer text for you to read at your own leisure, but it's also telling us in certain other cases which of the norms will actually preserve larger values versus small values. I'm just going to leave it to you to read that through. And of course, maximum norm, if I'm just looking for the maximum number of something, I'm looking for the worst scenario of something that could happen. Okay? Right. So it's just for fun. Okay? This is a circle of radius 1. Okay? And by definition of circle, I know that each point on a circle is the same distance, 1, from the center. And by distance, I mean this Euclidean distance, which means actually L2 norm. This is how a circle would look like in 1 norm. So if I was measuring distances with 1 norm and looking at the sum of absolute values only to be equal 1, then this is how a circle looks like. These points are on the circle. Let's put this point. If this is 1, this is 1 half, minus 1 half, 1 half minus 1 half, right? This point. Absolute value of 1 half plus absolute value of 1 half is 1. Therefore, this point is on a circle of radius 1 in norm 1. Same thing for here. This is 3/4 minus 1/4. Absolute value of 3/4 plus absolute value of 1/4 is 1. So this point, so this line is the line of points where that is true. Same here, same here, same here. This is a circle. Mind blown? Maybe. Maybe not. You're like, oh, that's boring. That's a percentage. Okay. And the same, so I'm excited about this. And this is actually how circle looks like in the max norm. So for all the points here between minus 1 and 1, right? Its x value is between minus 1 and 1, and its y value is minus 1, and its absolute value is 1. So that's the max. For all these points, max norm is 1. Same thing here on this line, that line. Okay. So this is a circle kind of has corners depending on the norm you're looking at. So it's the relativity of norms. All right. So there are some general norm qualities that they have to have. So I can have obviously many of them. They're always positive. They're really zero only for what I call a zero vector. So only when I only have all zeros, that's when I have norm is 0. That's an agreed rule. Okay? If I have a scalar multiplying my vector, I can just take the absolute value of the scalar and multiply by whatever norm. This just helps manipulating things. And there's so-called triangle inequality, where if I add two things, okay, the norm of that addition is less than or equal to than the 2 when I take two of them separately. So this is just a generalization. So anything that actually, any operation that I mark with these brackets like this, that satisfies this can apply to be a norm in mathematics. So all of those P norms actually satisfy this. So I'm just going to put this here. So the first place where norm norms will be useful. It's just figuring out the angle between two vectors. We're not going to get to it today because we're basically about to end the class. And this is where, so my doohickey here for writing and projecting on the screen will not be useful today, but it will be useful first thing next time. So I see you on Wednesday. So do let me know, has everybody checked whether you can make the first exam 1 and exam 2? No, not yet. Okay, so I will send a separate email to warn you to check your calendar. So it's going to be on evening on Monday. I'm forgetting Monday, March. Okay, I believe. Right. Anyway, so essentially, I will ask you to check that for me. Yeah. Yeah. So it is on syllabus. So I will ask you to check that for me, and I will send you a written reminder. And then if you have a conflict, like another exam, then we'll have to figure it out. Alright? And if it's anything like last semester, we'll have to figure it out, and figure it out, and figure it out,